In my last video, I discussed pressure temperature phase diagrams and how to apply those to real-world scenarios. In this video, we're going to continue that discussion, in this case with some specified prompts that I've already been granted. So let's go ahead and jump into these scenarios and kind of their solutions, as well as implementing them in some Python code. Alright, so prompt B1 discusses a container, and I'll go ahead and read the prompt for you guys here. It says a container with a total volume of 0.1 meters cubed. Well, that should jump out to us initially as a given. We know the total volume of our container here is 0.1 meters cubed. It also contains 1 kilogram of water. Awesome. With air in the headspace, okay, so now we know that there's two components to this kind of system here. I'm going to go ahead and denote the air givens in a different color. So air in the headspace at 101.325 pascals, and I'll call that the pressure of the air, as well as 298 Kelvin is the temperature of the air. And then it's sealed. To what temperature should we raise this container? So now we know that the temperature has to increase, which makes sense as we'll see in a second, such that the final pressure is 200 kilopascals. Okay, these are kind of our final conditions here. So we'll say the final conditions, the pressure final has to be equal to 200 times 10 to the third pascals, and the temperature final is going to be equal to, well, we don't know, that's what we're trying to solve for. Alright, so first there's a couple equations we should find here, but I'm going to go ahead and draw out our scenario. So I'm going to make the air components in this blue color, and I'll make the water components in, let's see, this darker blue color. Okay, cool. So initially we're given, we have an interphase in here at some point, right? With the mass of the water down here as a liquid, and then we also have the air in the headspace. And then at some point, and that air already has the initial temperature and pressure conditions as given in the problem scenario. So at some point this container is going to be closed. And now we have an isolated system. What this means is we can control the system based on how we control its surroundings. Amazing. So let's go ahead and derive kind of our first equations here. I'll do equations in a purple color. So we're going to say the total volume is going to be equal to the volume of the air plus the volume of the water. You'll see why I'm deriving the volume equations in just a moment. But as you can guess, it will have to do with the ideal gas law. Now, the total volume is equal to the volume of the air and the volume of the water. So, we know the total volume is 0.1 meters cubed. And we'll say that's equal to the volume of the air, which we don't know, plus the volume of the water. Now, we can figure out the volume of the water based on, I said I'll do water equations in this color, based on we are given the mass of the water. So the mass of the water is equal to 1 kilogram. If I multiply the mass of the water by density of the water, I will be given the volume of the water. So, the density of water, or I'll call it the rho of water, equals about 1 gram per milliliter, which, if I'm going to multiply that out then, I know there's 10 to the third milliliters in a liter, and I know that 1 liter is equal to 1 meter cubed, as well as I know that 10 to the third grams is going to be 1 kilogram. So that'll cancel with that. And basically what we're left with is about, it's going to be 997, but we're left with about 0.001 meters cubed per kilogram. And I did switch the orientation of the variables there, or the units I should say. So we'll say it's that multiplied by 0.001 will give us the final equation 0. I'm sorry, I messed up my units here. 0.01 should be to the hundredths place. 0.01 meters cubed of water is how much our volume of the water is. So I'll go ahead and throw that number into this equation here, and then we can solve for the volume of the air. There we are. Awesome. Now that we have our volume components, it's time to start looking at the pressures, because that's what we're trying to manipulate after all, is the final pressure. Therefore, I think it's pertinent to write out the total pressure of the container is going to be equal to the partial pressure of the air plus the partial pressure of the water in the headspace. Okay, cool. Now that we have these two things, we need to derive the equations for the pressure of the air and the pressure of the water. Okay, so with this, I think the pressure of the air is the more relatively simple one, so we'll start with that. The pressure of the air is at low pressures, and we're going to consider atmospheric pressure, or 101.325 pascals, a relatively low pressure. Air behaves similarly to an ideal gas, meaning it will therefore follow the ideal gas law, where PV is equal to nRT. In this case, we are solving for P, so we will say the pressure of the air is equal to the volume of the air, the moles of air, multiplied by the ideal gas constant, multiplied by the temperature of the air, all over the volume of the air. Okay, cool. We have all of these parameters here, except for one. And that parameter that we don't have is going to be the moles of air in this case. The moles of air we can find based upon its initial pressure and initial temperature. So we're just going to use the ideal gas law again. However, given the initial pressure and temperature, we are going to solve for the moles of air present once the container is sealed initially. So the moles of air, which we're solving for given with our initial conditions, is going to be equal to the initial pressure of the air multiplied by the volume of the air over the ideal gas constant over times the temperature of the air. And this here we have, and we could go ahead and solve for that. However, if we are to multiply this in to the equation, then we would notice that some of our variables are going to cancel out. So, the pressure of the air here, let's see. If I'm going to put this in, then what's going to cancel out? If I'm going to put this in for the moles of air in this equation, what would initially cancel out would be the ideal gas constant. The temperature of the air here is going to be equal to a constant, 298 degrees Kelvin. So that would not actually cancel with the temperature of the air in the other case, which is going to be variable. The volume of the air, however, is going to stay constant, so it will go ahead and cancel out. And then again, the pressure is an actual value, so it will not cancel out. 101.325 pascals. So then, I'm going to drop this equation down to here, and we will then be solving, actually, I'm sorry, I'm going to drop it one line below. So I'll say the pressure for the air as a function of temperature is going to be equal to 101.325 over 298 multiplied by the temperature of the air. We could also write this as the initial pressure times the ratio of the two temperatures, the temperature of the air over the initial temperature, which is how we're going to use it when it's implemented in our code. So that makes that kind of fun. Okay, cool. Now let's move on here to the partial pressure of the water in this scenario. First, I think it's important to mention that the partial pressure of the water, we're looking at the interphase here. And I discussed the interphase in my previous video, so I'm not going to jump into it too far. However, it is important to mention that that part, or that interphase in this actual applicatory scenario, is going to be equal, is going to follow the same conditions as a pressure-temperature phase diagram. So, knowing that, let's go ahead and write our equations for the partial pressure of water here. Okay, so the partial pressure of water is actually going to be equal to the saturation vapor pressure of water. The reason for this, as I attempted to explain poorly earlier, is that at the interphase you're going to have the vapor-liquid equilibrium conditions that would be present along the vapor-liquid equilibrium curve. Therefore, we can denote the pressure of water as the saturation liquid vapor pressure. Okay. Now, we need to solve for that saturation vapor pressure. And the way that we are going to actually come about by doing this is by using another equation that is kind of in our tool belt at this point in chemical engineering. And I'm going to go ahead and write all of water's things down here. So again, I said the partial pressure of water is going to be equal to the saturation vapor pressure of water at that specific temperature. And this equation is going to be the Anton equation. The Anton equation here. What the Anton equation in its most general form states is that the log base 10 of a pressure is equal to A minus B over the temperature plus C, where A, B, and C are constants. Now, a limitation of the Anton equation is that it applies to very specific temperature ranges, and so these constants A, B, and C will change for those particular ranges. So because we're actually looking for the saturation vapor pressure as a function of temperature, we can go ahead and rewrite this equation as such. There we go. And now we have that saturation vapor pressure as a function of temperature. Similarly, we also have the pressure of air, the partial pressure of air, as a function of temperature. So let's write the entire thing down here. So the total pressure of the container, or P total, is going to be equal to the initial pressure of the air multiplied by the ratio of the changing temperature over the initial temperature plus 10 times 10 to the A minus B over T plus C, which again is the saturation vapor pressure of water. Okay, cool. Now, given this equation, it is now time to actually solve for what that final temperature is going to be. Remember, we want our final pressure to be equal to 200,000 pascals. We can also write this as 200 e to the third or 2 e to the sixth. Any of those variations would work in this case. Okay, cool. So we've derived the equation. I think it's time to head on over to B2 and jump into kind of our Python code in order to actually solve this guy. So I'm going to solve this in Colaboratory. And I'll start out a new notebook here. So let me widen this out here. Awesome. Give me just a moment to fix this up. Okay. And here we are. Cool. Sorry about that. Let's go ahead and implement these equations into our Python code here. So the first thing that we're going to do is we're going to actually use a from SciPy .optimize. We're going to use their root solver. So we'll say import root. And then we'll also go ahead and import NumPy. Both of which are going to be useful libraries in this scenario. Okay. Now we need to go ahead and set up our two equations. And then we're going to use a root solver to solve the root, or when the temperature is going to match. So, first I guess we'll go ahead and this will be our Anton equation here. So, we're going to need the values for A, B, and C in this case. And then we'll go ahead and define a function. We will call this, I'll call this AntEQ, short for Anton equation. And this will use temperature as kind of its input here. And then we will go ahead and say that the Psat for water, or the saturation vapor pressure, is equal to 10 to the exponent of A minus B over T plus C. Now, For the values of A, B, and C, I'm just going to go ahead and look them up. I'll look up Anton equation, and water comes up almost immediately. So, remember, I said it does only account for a specific temperature range. In this case, the minimum temperature would be 99 degrees Celsius, the maximum is 374. I can assume that it will be in that range just based on an initial guess for the problem. So, now we have all of those, and we can go ahead and do that function there. Next, we need to go ahead and define a function. We will say this will be to find the pressure of air here. And what that is going to require as an input is the initial temperature as well as the initial pressure. And we were already given those in our problem, so I'm just going to go ahead and type those in. A nice thing to do would be to add units here. However, this isn't obviously necessary in the grand scheme of solving the equation. I'm going to go ahead and define this function, and I'm going to call it something along the lines of partial pressure of air as a function of temperature. Awesome. In this case, we will say that's equal to, I will call pressure of air equal to Pi multiplied by T over Ti. Wonderful. Now, I just need some sort of function in order to put these together. So I will call this the functions added, or this is going to be the equation that combines both of our functions here in order to find the P total function. So we'll call this P total as a function of temperature. And what we're just going to go ahead and do here is I'm going to say define the function P total as a function of temperature, and P total is going to be equal to P air plus P sat. Okay, now that we've defined our function here, the last thing we are going to have to do is just go ahead and find the root. So we'll say root of P total, and then we just need to provide some sort of initial guess here. So for my initial guess, I'll go ahead and say 350 as just a guess, and then that will go ahead and solve it. Alright, so we did have a little bit of an error come up here, with that error being that P sat was not defined. So we just need to go ahead and define P total here. I believe I forgot to return these as the actual values of the function. What do we have here? I guess I don't need to define that as a variable. Wonderful. So then we're just going to go ahead and define P total here, and we'll say it returns the pressure of air as a function of temperature plus the Anton equation as a function of temperature. And then remember when we wrote our initial equation, we said it was equal to 200,000 pascals. In this case, we're going to have to subtract that off in order to make the root finder work. When that function is equal to 0, as it is in the case where you subtract 200,000 from both sides, the root finder will then work. So we'll just go ahead and solve that. And we have our final answer here as about 323.84 degrees Kelvin, which, if we were to check with our initial temperature of 298, that does seem to work. So we have about 323.84 degrees Kelvin as the answer here. Boom! I changed clothes. So now that we've finished B2, it's time to move on to B3. So let's go ahead and I'm going to go ahead and read that so that we're all on the same page. We're just repeating the calculation from B1, so we're using basically the same system here. And this time, instead of the temperature being the only unknown in this scenario, we also have to figure out what the total volume of the container is, since it's unknown. But we are given the statement that 0.3 moles of water vapor is desired in the vapor phase. Everything other than that is about the same. So we can go about solving this in virtually the same way. Now, I think it's important to note, first off, that there are two big unknowns in this scenario. The first of which is still the temperature, or the final temperature as I'm going to denote it. We don't really know what that is still. The other thing we are kind of unsure of here is the total volume of the container. And in this case, the total volume could be around the same amount, or it could not be. We really don't know. So, given these two unknowns, we need to derive a system of equations for which we can solve these two variables, or parameters here, rather. So the first equation is going to look relatively similar for finding our temperature as this equation. So I'm going to go ahead and copy it down here. There we go. Now, there's going to be one major difference between this equation and the one we used earlier. Remember, this is, or I'll use different colors here, this kind of chunk of the equation here is the saturation vapor pressure of water, and then this kind of chunk of the equation here is the final pressure, partial pressure rather, of the air. Now, the saturation vapor pressure for water is going to stay constant, as the interface we're assuming isn't really changing here. Therefore, we're going to have that same interaction as we did in the initial system. However, for the partial pressure of air, there is a slightly different calculation that needs to be made. The reason for this is that we do not know the total volume. Therefore, when we go ahead and derive our equation for the partial pressure of air, the volume will not cancel out completely, and we will not have as nice of a ratio here. So let's go ahead and try to derive this equation again. Remember that the pressure of the air, we're still using that ideal gas law, is going to be equal to the moles of air multiplied by the ideal gas constant multiplied by the initial temperature. All of this then will be divided by the volume of the air. Now, when I say volume of the air, what I really mean is the volume of the vapor phase, in which water is constantly condensing and evaporating into and out of it. I'm saying volume of air here because water vapor is indeed a component of the air that we generally see in our atmosphere. So, do note that the volume of air does not exclude the water vapor that is continuously being interchanged within that system. Okay, so this is really as far as we can go in deriving our equation for the pressure of air, because we have no way of calculating this volume of the air. Remember earlier what we did was we subtracted the volume of the water from the total volume. However, in this case, that is not applicable. So, other than that, this equation will stay relatively the same. And because we have the same final pressure, when we end up doing our root function, we're going to subtract that same final pressure. And then we can set this equation equal to 0. Now, for our other equation, we have to kind of go back and remember a little bit of the total volume factors in which how can we solve for that total volume. So the other big equation, I guess, in this scenario is kind of using the ideal gas law and subtracting from it our given, or the moles of water we require in the vapor phase. So, in other words, I guess we can write the second equation. I'll go ahead and do it in red here. The second equation we can write as the total volume is going to be equal to the volume of the vapor phase, and again I'm just writing that as the volume of the air, plus the volume of the water. Now, because we can write that, we can write volume of air and volume total interchangeably. These are interchangeable equations here, right? I can rewrite this algebraically as volume of the air is equal to the total volume minus the volume of the water. I can then kind of use the volume of air as the unknown with which to write my second equation here. And for that, I will again just use the ideal gas law. So, the volume of the air is going to be equal to, well, we know that we want 0.3 moles of water in there, right? So that makes sense. And then that's going to be equal to the ideal gas constant multiplied by the moles of air multiplied by the temperature. In this case, it'll be kind of the final temperature, because that is our second unknown, right? Over the pressure. And in this case, our pressure will be the final pressure, which we can solve for by having temperature. And then again, to make that a root, we will simply subtract 0.3 moles from both sides, setting our equation here equal to 0. With all of this, I think it's time we head back into co-laboratory and finish coding out this scenario in order to solve for our variables. So, I'll leave our equations here again. Our equations. So, let's go ahead and define another final function. For this one, I'm just going to say, this is technically part B4, so I'll call it B4 underscore solve. And what we are solving for, now remember, we're solving for two unknowns. Since we're solving for two unknowns, that will mean that this has to be a vector. So, let's go ahead and call it vector as the input. Oops, didn't mean to run that. So then, with our vector input, let's go ahead and break down that vector into its components. Its components are going to be the temperature, final, as well as the total volume, right, is going to be equal to our vector here. Now, the total volume is equal to, as we said earlier, the volume of the air plus the volume of the water. Now, we didn't define the volume of the water earlier, so in this sense we need to go ahead and define the volume of the water. It's going to be equal to the mass of the water divided by its density. Similarly, we're going to need to define the mass of the water then. And in this case, it will be 1 kilogram. Okay. So then, let's kind of work backwards here and think about what we need to return. Well, we need to return both of our functions here. So the first function will be the ideal gas constant multiplied by the moles of air multiplied by the final temperature. All of this divided by here the final pressure. Or we could rewrite this even as P total as a function of T. Our other function here, minus, I guess, I almost forgot that we were making this a root function, which means we need to subtract our moles of water in the vapor phase. So I'll just call this water vapor, and it should be in moles for this function. And we wanted 0.3 in there. Alright, that should be kind of our first one there, and that reminds us that we need to go ahead and define our ideal gas constant at 8.314. Similarly, we also need to define our moles of air. Alright, so our moles of air should be relatively straightforward here. That's just going to be basically using all of the initial conditions from the first scenario. So it's going to be our initial pressure, and then our volume of the air divided by, I'm sorry, these are going to be multiplied together, divided by the ideal gas constant, multiplied by the initial temperature. Alright. Next then, what we are going to go ahead and do is define our second equation, so moles of air multiplied by the ideal gas constant, initial temperature, all over the volume of air, plus we can just go ahead and use our function again there, and subtract from it 200,000. If I were to go ahead and run that, it looks like it works. However, our volume of air has not been defined. So, in order to kind of alleviate this issue, what we need to do is kind of return to our conceptual phase and understand why the volume of air has not been defined. In this case, we can actually rewrite our function on the bottom there in red on this document. We can rewrite that in terms of and solving it as equal to the pressure. So basically we're just going to exchange the pressure value with the volume of air value. then all we should need to do here is just go ahead and solve our function. So we'll just go ahead and solve this. Our initial guess for the temperature can be something around 350, as it was in the previous one, and our initial guess for the volume can be something around what it initially was in our first question at 0.1. And of course, we are going to have an error come up as we haven't defined the error yet. So then, let's go ahead and define the error, and we can go ahead and do that right here by kind of switching around our variables here. We can just say that, again, the air is going to be equal to the total minus the volume of the water. And then we will come up with our solution here. So it looks like our initial guesses were a little invalid. So let's kind of try and shake them up here in order to get a slightly different scenario. So I'll just go ahead and change my initial guess for temperature. And again, it's kind of coming up with a slightly invalid guesses there. No. So our initial guesses are giving us slightly obscure answers. So that does make us want to go back and kind of troubleshoot our function, right? So in looking at this, we can discern that it looks like our ideal gas constant is on the wrong side of the equation there. Ah, there we go. So now we have much better initial guesses as well, and this will go ahead and solve our function with our final volume being or our final temperature rather, being equal to 320, a spot-on guess, as well as our final volume actually also being a very correct guess at 0.1 for this equation. And so I hope this video has been helpful in some sense, as we have now kind of solved two of these scenarios in Python, as well as taking you through the derivation for these equations. Thanks for watching. As always, goodbye.